Alright, so good evening everyone. My name is Avik Mukhopadhyay and I am one of the TAs for the course on digital signal processing. So the agenda for today is to discuss some sample problems related to the contents covered in week number 6. So in week 6, if you remember, the topics that were covered included the initial value theorem and the final value theorem for the Z transform. The statement for Parseval's theorem was discussed. Then we also saw how multiplication in the time domain translates to circular convolution in the frequency domain and stuff like that. Then we investigated few methods for finding the inverse Z transform, and the first method, which is the popular one, also known as the partial fraction expansion method, was used to compute the inverse Z transform. We saw some examples, and then the second method that we studied was the power series method, and we saw that the power series method can also be thought of as the long division method. And finally we also explored the contour integral method. Okay, so with these contents and concepts in our mind, let's get started with today's session. So all right, so I hope people can see my screen. So I hope question number 1 and 2 is visible to everyone. Let me just quickly check once if the recording is going on. Yeah, it's going on. So yeah, so the first question is based on the concept of initial value theorem. So the Z transform x of z is given in the question. X of z is equal to z square plus z plus 1 divided by z plus 2 times z plus 1, and we have been asked to find the initial value of the time domain signal x of n, that is x of n evaluated at n equals to 0, which is x of 0, using the initial value theorem. So, and by the way, the underlying assumption here is that, so you know, when we prove the initial value theorem for Z transform, what is the assumption that we take? So we assume that the time domain sequence, which is x of n, is a causal sequence. Okay, that is x of n is 0 when n is less than 0. So it is already assumed. We will assume that that particular condition holds true, and that is why we are able to apply the initial value theorem to find x of 0. Alright, so I'll just write it down. Okay, right, so this is digital signal processing, and we are looking at week number 6 and the first question. So in the first question is based on initial value theorem, and so the given Z transform is x of z equals z square plus z plus 1 whole divided by z plus 2 times z plus 1, right? And we need to find the initial value of the corresponding time domain sequence, that is, what is the value of small x of 0. And the assumption which we keep in our mind while applying the initial value theorem is x of n is 0 for n less than 0, that is, x of n is a causal sequence. Okay. So how do we find the initial value? So if you just refer to the lecture notes, if you look at the statement of initial value theorem, we have a general formula. So for a causal sequence, x of 0 is given by limit z tends to infinity capital X of z, right? So what do we have? Limit z tends to infinity, what is capital X of z? Z square plus z plus 1 divided by z plus 2 times z plus 1. Okay. And now the standard method for evaluating such limits is to, since z tends to infinity, so we know that 1 by z or z inverse tends to 0. So what we can do is we can multiply the numerator and denominator by z to the power minus 2. Okay, and then we can put 1 by z tends to 0, okay, and replace such terms by 0. So let's do that. So limit z tends to infinity implies limit 1 by z tends to 0 or z inverse tends to 0. Okay, so limit z inverse tends to 0, and we are just dividing the numerator and denominator by z to the power minus 2. So what do we get? So the first term in the numerator, it becomes 1, then we have this and this, and in the denominator we can just divide the first factor by z inverse and the second factor by z inverse separately. So the overall factor by which the whole denominator is divided is z to the power minus 2. So if we do that, we get 1 plus 2 times z inverse times 1 plus z inverse, right? And we can simply just substitute z inverse as 0. Okay, so z to the power minus 2 is also 0, right? Okay, so we get 1 plus 0, similarly 0 divided by 1 plus 2 times z inverse is again 0 times 1 plus 0. So we have 1 divided by 1, which is 1. So the initial value of the time domain sequence, which is x of 0, is 1. Okay, this is the final answer. So it was very simple, formula based, and similarly we have the second question here. Okay, right. So the second question is a similar one. It's just uses the concept of final value theorem. So we need to find x of n at n equals to infinity. So we need to find the value of x of infinity given this z transform x of z. So and again, like we saw in the previous case for initial value theorem, the assumption that we have for initial value theorem is that x of n is a causal sequence, that is x of n is 0 for n less than 0. Similarly, for final value theorem, if you recall your notes, the assumption that we take is x of n is a right sided sequence. You can think of it as a causal sequence. It's a right sided sequence that beyond some capital M integer, x of n is 0. Okay, so it's a right sided sequence. So I mean, below all for that is x of n is 0 for n less than capital M, let's say, where capital M is some integer. So from m plus 1 index onwards, it's non-zero. So it's a right sided sequence. So we will keep that assumption in mind and just apply the formula for initial value theorem. So let us write it down first. Second question, looking at the second question. So second question is based on final value theorem. Oops. Okay, so we have been given x of z, the z transform as z plus 1 divided by 3 times z minus 1 times z plus 0.4. Okay, and again for final value theorem, the assumption is, like I said, x of n is 0 for some n less than capital M. While proving the final value theorem, we have looked at this assumption, right? You just recall your lecture notes. So it's a right sided sequence basically. Okay, just a second. Yeah, so now if you remember the formula for final value theorem, so x of infinity is given by limit z tends to 1 minus z inverse times capital X of z. Okay, now so since there is a multiplicative factor of 1 minus z inverse, so and our given z transform x of z is in the form of z rather than in the form of z inverse, so we will try to convert that x of z in terms of z inverse, so that there is a possibility of this 1 minus z inverse coefficient term sitting here in the limit to be get cancelled by the other terms of similar form. Okay, so we will try to express x of z in terms of z inverse. Okay, so let us do that. So x of z is this, so I can also write x of z as, so here similarly like we did for the previous case, we multiply the numerator and denominator by z to the power minus 2, right? And if we do that, we get z inverse times 1 plus z inverse divided by 3 times 1 minus z inverse times 1 plus 0.4 z inverse. Okay, right, and we will just substitute this expression for x of z in this limit. So let's do that. So we get limit x tends to z tends to 1 minus z inverse, and what is x of z? X of z is okay. So clearly there is a cancellation. So we have this 1 minus z inverse term getting cancelled. So this gets cancelled by this, okay, which is why we actually expressed x of z in terms of z inverse. We wanted this cancellation to happen. So let's proceed further. I will go to the next page. So which is equal to limit z tends to 1, and once that 1 minus z inverse term gets cancelled, we are left out with this divided by 3 times 1 plus 0.4 z inverse. Okay, and now it's just substituting z equals to 1 in the expression. So we get 1 plus 1, so z is 1, so z inverse is also 1, and 3 times 1 plus 0.4. okay, so what do we get? So this is 2 by 3 into 1.4, so which is 2 by 4.2, which is 0.476, and it's approximately, you can round it off to 0.48. Okay, and now so you can also verify your answer by finding this x of 0 for the first question as well as for the second question. You can also verify your answer by explicitly first evaluating the inverse Z transform to get the time domain sequence x of n. So you know the methods for finding the inverse Z transform. So like partial fraction expansion or long division, whichever you want, whichever is convenient for the problem, you can use that and come up with the expression for x of n first, and then you can just substitute the value of n. If it's the initial value, put n equals to 0. If it's the final value, put n equals to infinity. So and in this case, since the ROC is not mentioned, so that's why we take the assumption here, right? For the first question, we take the assumption that it's a causal sequence. X of n is 0 whenever n is less than 0. And for such a causal sequence, we know the ROC is exterior of a circle, right? It lies outside a circle. So the poles of x of z in the first question are clearly at z equals to 2 and z equals to minus 2 and z equals to minus 1, correct? So there are like multiple possibilities depending on these pole locations. There are 3 possible ROCs, right? But since it's a causal sequence, so it will be outside of a circle, and the largest circle here is the circle that contains the point z equals to -2. So it's a circle of radius 2, correct? So mod z greater than 2 will be our ROC, okay, by assumption. So if you choose your ROC as mod z greater than 2, check that the x of n that you will get. So I'm just using a rough space here. Okay, so you can check that the x of n that you will get is -3 times -2 to the power n minus 1 times u of n minus 1 plus -1 to the power n u of n plus 2 times -1 to the power n minus 1 times u of n minus 1. So this is the time domain sequence that you are supposed to get, okay? So kindly check it. And so just to verify your answer, you can also put n equals to 0 in this expression for x of n, and clearly if you put n equals to 0, the first term which contains u of n minus 1, they will vanish because u of minus 1 is simply 0. Only the middle term will persist. So and it takes the value -1 to the power 0 times u of 0, which is 1, and this is exactly what we got as our answer, 1. So this is a way to verify your answer, okay? And similarly for the second problem as well, you can also check. You can take the inverse Z transform. You can use partial fraction expansion and find the expression for x of n, assuming that it's a right-sided sequence. So of course here also the ROC will be outside of a circle, right? So keeping that in mind, so here you can take the ROC to be, the poles are at z equals to 1 and z equals to 0.4. So the ROC will be mod z greater than 1, you can consider. So if you do that, you will find that x of n will be something of the form 1.4285 like this, okay? So yeah, please check this, okay? And here also if you put n equals to infinity, you will be able to get a value which is approximately 0.48, which is what we got using the direct application of final value theorem formula. So just check it. Anyway, so right, recording is going on fine. All right. So we are done with the first question and the second question, and now let's move to the third question. Okay. So the third question is again based on the concept of finding the inverse Z transform using partial fraction expansion method, and we have been given this formula, very famous formula. So this relation between the time domain sequence a power n u of n and its Z transform, which is given by 1 divided by 1 minus a Z inverse with the ROC as mod Z greater than mod a. Okay. Using this relation and also the concept of partial fraction expansion, we need to find the inverse Z transform of this given x of z, capital X of z, Z transform. Right. So capital X of z is of the form 1 minus 1/3 Z inverse whole divided by 1 minus Z inverse times 1 plus 2 times Z inverse with the ROC as mod Z greater than 2. Okay. Right. So let's write it down. Okay. So question number 3. Okay. So the task is to use partial fraction expansion to find our time domain sequence x of n, and we have been given this known Z transform relation, okay, a power in u of n as the Z transform, which is given by 1 minus a times Z inverse, and the ROC is mod Z greater than mod a. Okay. And the given Z transform in our question is capital X of 0 equals 1 minus 1/3 Z inverse divided by 1 minus Z inverse times 1 plus 2 times Z inverse. Okay, and the ROC is mod Z greater than 2. Okay, cool. So how do we solve for small x of n using partial fraction expansion? So if you recall your notes, this x of z is in the proper form. Okay, it's known as the proper form. Why? Because the order of the numerator is at most less than or equals to the order of the denominator. So here the denominator is z to the power minus 2, whereas in the numerator you have z to the power minus 1. So yeah, so and so how we solve this kind of problems is that we can just, since the denominator is already factorized into 2 terms, so we can just express this whole x of z as the sum of 2 terms. Okay, and in each of those terms the denominator will contain the individual pole terms. Okay, so what I mean is we can express this, we can express this whole x of z as some a divided by 1 minus z inverse, a can be any constant, plus b divided by 1 plus 2 times z inverse. Okay, so sum of the pole terms. Okay, so the first pole 1 minus z inverse is weighted by some constant a, and the second pole term, which is 1 plus 2 z inverse, is weighted by another constant b, and they are also known as the residues, right? And now we can compare these two, we can compare these two expressions for x of z, and we can come up with the values of a and b. Okay, so why we are doing this is because once we know the values of a and b here, the constant values, once we are we know their values, then these individual terms in the summation is a known form of z transform, right? Some constant by 1 minus z inverse. So that's exactly similar to this given relation, right? 1 by 1 minus a times z inverse, and its corresponding inverse z transform, the time domain sequence is a power n u of n. Okay, once we know this a and b values, we are done. We can easily find x of n. Okay, so that's why we express it as a sum of two terms, where each term contains a pole in the denominator. Okay, so let's proceed further. So if we take the LCM again here and cross multiply in the numerator and equate it with the original expression of x of z, we can write a times 1 plus, so here we are assuming, okay, c, let this can be expressed as this form, and now we will find a and b such that this condition holds. So a times 1 plus 2 times z inverse plus b times 1 minus z inverse equals, what is in the denominator in our original expression of x of z? It is 1 minus 1/3 z inverse. Okay, and let us label this by equation 1. Okay, now we can simply just put some values of z inverse, okay, and come up with the values of a and b. So first we can substitute, let's say z inverse equals to 1. Why? Because if we substitute z inverse equals to 1, the coefficient of b on the LHS becomes 0, so that term vanishes. We are only left with the term containing a. Okay, and on the right hand side we'll get some value, and we can find the value of a. And similarly, to find the value of b, we can make the coefficient of a as 0 and then find the value of b. Okay, so let's do that. So first we will putting z inverse equals to 1. So this is an identity, it's valid for all z inverse, right? So putting z inverse equals to 1 in equation 1, we get, so here we get 3 times a, right, and b will vanish, and on the right hand side we get 1 minus 1/3, which is 2/3, that is a is 2 by 9. Okay, so we got the value of a. Now similarly we can put z inverse equals to, now we want to make the coefficient of capital A in equation 1 to be 0. So for that 1 plus 2 z inverse, which is the coefficient of A, that must be 0. So we can put z inverse as minus half. So let's do that. Okay, so the coefficient of b becomes 1 minus minus half, which is 3 by 2 times b, so 3b by 2 equals, on the right hand side we get 1 minus 1/3 times minus half, which is 1 plus 1 by 6, which is 7 by 6. So 7 by 6, so b comes out to be 7 by 9, just check. Okay, so we found the value of a and b, and we will just put it in this expression, a by 1 minus z inverse plus b by 1 plus 2 times z inverse. Okay, we'll just substitute that. So therefore capital X of z is two by 9. We can bring the constant in front. Okay, so a is 2 by 9, it was in the numerator, I am just taking it in front. So 1 by 1 minus z inverse. Similarly for b also we can take it in front, and we have 1 by 1 plus 2 times z inverse, and mod z is greater than 2 is already mentioned. So now what to do? We already know this relation, given relation, a power n u of n has a z transform 1 by 1 minus a z inverse. Okay, so we will use that relation. So obviously this first term here, this term, it has an inverse z transform equal to how much? So the constant will remain as it is, 2 by 9 times. So here it's of the form 1 by 1 minus a z inverse, where a is 1. So we have a power n u of n, a is 1, 1 power 1 is simply 1, so it's u of n. Okay, similarly for the second term, its inverse z transform is given by, the constant will again remain as constant, times. So here we have again z transform of the form 1 by 1 plus a z inverse. So here we have a plus term. Okay, plus is in a z inverse. So here a is minus 2. Okay, so and what is a power n u of n? It's minus 2 power n u of n. Okay, so minus 2 power n u of n. Okay, And now simply by linearity of Z transform, we can write our overall x of n as the sum of these two terms. Okay. That's it. That's it. So this is our required inverse Z transform, that is the time domain sequence, okay, which was being asked in the question. So we have used the partial fraction expansion method to find x of n from given capital X of z. Okay, great. So let me check if recording is going on. Yes, it's going on. Okay, so now coming to the fourth question. Again, in fourth question we have three subparts, and we have been given the expression for this Z transform capital X of z, and again we need to find the corresponding time domain sequence, and we need to use the method which has been mentioned in each of the cases. So in part A of question number 4, we have been asked to use partial fraction method for finding x of n. We have been given capital X of z, and also we have been mentioned that x of n is absolutely summable. I am talking about 4a. So we have been given capital X of z, and also we have been mentioned that x of n is absolutely summable. Using this information and using partial fractions, which has been mentioned for 4a, we need to find the corresponding x of n, the time domain sequence. Okay, so let's see how to do it. Okay, so we are in question number 4a, and in 4a we need to use partial fractions. It has been mentioned that we need to use partial fractions. Okay, and the given Z transform is 1 minus 2 Z inverse divided by 1 plus 5 by 2 Z inverse plus Z to the power minus 2. Okay, and we have been mentioned additionally that x of n is absolutely summable. Sorry for my bad handwriting. So yeah, right, 1 minus 2 Z inverse, 1 plus 5 by 2 Z inverse plus Z to the power minus 2. Yeah, okay. Right. So again, the denominator has the order Z to the power minus 2, so it's a quadratic in Z inverse, and in our previous question x of z was already in a factorized form in the denominator, right? 1 minus Z inverse times 1 plus 2 Z inverse, and then we just wrote it as sum of those two individual factors, right? So one step was already done for that question. Here we need to do that initial step, so we need to first factorize the denominator here. Okay, so some we have to factorize it in some form, some gamma minus z inverse times, let's say, some delta minus z inverse, okay, to determine the pole locations. Okay, so let's do that. Let's factorize the denominator so that we can then use our partial fraction method and write it as like we wrote for the previous problem, a divided by the first term plus b divided by the second term, second pole, and then we find the values of a and b. So how do we factorize the denominator here? 5 by 2. Okay, 5 by 2 times z inverse is sitting in the middle. So 5 by 2 can be written as 2 plus half. Okay, and if you multiply 2 and half, we get 1. So here the first constant term is 1, and here the coefficient of z inverse is also 1. Their product is 1, and 2 and half, their product is also 1. So 2 and half, so 5 by 2 can be written as a sum of 2 plus half, and that will be actually useful in factorizing this whole expression. So let's write 5 by 2 as 2 plus half. I hope this factorization is not something new to you. You are already aware of it anyways. So one plus, I can write it as 2 z inverse plus half z inverse plus z to the power minus 2. Okay, which is 2 z inverse divided by 1 plus 2 z inverse. I can take half z inverse as common. So half z inverse times 1 plus 2 z inverse. Okay, so we have 1 minus 2 z inverse whole divided by 1 plus 2 z inverse becomes a factor, and the other factor is 1 plus half z inverse. Okay, yes, is this right? Yeah, so so we have successfully factorized the denominator. Okay, now now it's just the same process that we used for solving the previous question. So we can now write it in terms of a and b. Okay, sum of two terms. So let's do that. So x of z is, we got 1 minus 2 z inverse whole divided by 1 plus 2 z inverse 1 plus half z inverse. Okay, and now we can just write it as some a by 1 plus 2 z inverse, the first factor corresponding to the first pole, plus some b times the second term or the second pole. So say this is true. So now we will find the value of a and b such that this holds true. So if we just again cross multiply the terms and equate the in numerator, we get a times 1 plus half times z inverse plus b times 1 plus 2 z inverse equals 1 minus 2 z inverse. Okay, right, let me label this as equation 1, and again we will just put z inverse to be some values such that one of the terms, either a or b, gets vanished, and we can find the value of the remaining term. Okay, so let's do that. Let's first find the value of a. For that we need to vanish b, and for eliminating b we need to equate its coefficient to be 0. So we put z inverse equals to minus half, correct? So first let us put z inverse equals to minus half in equation 1. So we will get 3a by 4 equals to 2, or a equals 8 by 3. Okay, just check this. Okay, we got a equals to 8 by 3. Great. Similarly, we can now find the value of b. For that we need to eliminate a. For eliminating a we need to equate its coefficient to 0. So for that we need to put z inverse equals to minus 2, right? So let's do that. I'll go to the next page. So if you do that, if you put z inverse equals to minus 2 in equation 1, you will get something like minus 3b equals 5, or b is equal to minus 5 by 3. Okay, so we got both the values of a and b. Now we need to just plug in these values of a and b in this form here. Okay, here a by 1 plus 2 z inverse and b by 1 plus half z inverse. Okay, so let's do that. So therefore x of z is 8 by 3. So I am taking the value of a, which is 8 by 3, which was sitting in the numerator. I am taking it in front, and we have 1 sitting in the numerator, and we have 1 plus 2 z inverse in the denominator. Similarly, we are taking b, which is minus 5 by 3, in front. We have 1 by 1 plus half z inverse, correct? Okay, so now to find x of n, we need to find x of n. That's okay, but for that we need to also have the knowledge of what? The ROC. Okay, so this Z transform is of the form some 1 by 1 minus A inverse, which is a known form, well and good, but it can lead us to different time domain sequences depending on the ROC. Okay, so that is why we need the knowledge of ROC. Now here we know that the ROC is governed by the pole locations. The ROC is bounded by the poles. So here, if you observe these two terms, the pole locations are at, the first pole is at z equals to minus 2, right? and the second pole is at z equals to minus half. Okay, so pole locations at z equals to minus 2 and z equals to minus half. Okay, and now depending on these pole locations, there will be 3 possible region of convergences, ROCs. Why 3? Because, so the possible, you should know why 3. It's nothing complicated about that statement. So possible ROCs are, so okay, we got z equals to minus 2 and z equals to minus half as 2 pole locations. Now based on these points, there can be 3 possible regions. So one possible region is mod z. Okay, remember whenever we talk about ROC, we take the mod. Okay, because we are dealing with the radius of the circle. So z equals to minus 2 means it's a circle of radius 2. Similarly, z equals to minus half means it's a circle of radius half. Okay, so the possible ROCs would be mod z greater than mod of minus 2, which is 2. Okay, that is exterior of the circle of radius 2. That is one possibility. The second ROC could be within these two values, like mod z greater than mod minus half, which is half. So half less than mod z less than 2. Okay, so it's an annular region. Okay, you get it. Similarly, the other ROC could be mod z is less than half. So it's interior of the smaller circle of radius half. Okay, within the circle of radius half. So these are the three possible ROCs for these 2 pole locations. Okay, so the 3 possible ROCs are, first we have mod z less than half. Okay, then we have the annular region. Okay, and finally we have mod z greater than 2. Okay, fine. Now which one is the ROC that we should go with? Okay, is it the first one, is it the second one, is it the third one? Okay, there are 3 possibilities, but only one should be true. This is where the additional information which is given in the question will help us. So let's go back. So in our question there was one additional information given, which is x of n is absolutely summable. I am again going back to the question also. So in 4a you see it is mentioned that x of n is absolutely summable. And now once you hear this statement that x of n is absolutely summable, it should ring a bell. If you are able to recall it, then it's great. If you are not, then you are encouraged to revisit your lecture notes, and you will find that whenever the time domain sequence x of n is absolutely summable, it implies that the unit circle, that is z equals to e power j omega or mod z equals to 1, this unit circle is included in the ROC of capital X of z. Okay, it has been proved in the lectures. So now we know that the ROC should contain mod z equals to 1, the unit circle. Now tell me, out of these 3 possible ROCs, which of the following is our required ROC that contains the unit circle mod z equals to 1. It's clearly the middle one, right? This one, this one, this particular ROC includes mod z equals to 1, the unit circle. Okay, so what was the logic? So it was given that x of n is absolutely summable, and we know from our lectures, okay, sorry, so therefore ROC of capital X of z should include, it includes the unit circle, which is mod z equals to 1. Okay, and therefore out of the 3 possible ROCs, the ROC of capital X of z is the middle one, okay, which is half less than mod z less than 2. Okay, is recording going on? Yeah, it's going on. Let's continue. Okay, great. So we have now found the ROC as well. Now, so x of z we had simplified till this point here. We had expressed it in terms of sum of 2 terms containing the poles in the denominator. So let's now find the inverse z transform of these individual terms in the summation, and then we will use linearity to find the overall x of n. Okay, so the first term in x of z was 8 by 3 times 1 by 1 plus 2 z inverse. Let's try to find the inverse transform of this first term. Okay, so we have 8 by 3 times 1 by 1 plus 2 z inverse. So given this ROC that we just deduced, mod z lying between half and 2, okay, so this will have, so mod z is less than half, so this term that we are dealing with here, 8 by 3 times 1 by 1 plus 2 z inverse, it has a pole at z equals to minus 2, which is mod z equals to 2, okay, and the ROC is mod z less than 2, okay, ROC is interior of this pole, okay. So definitely its corresponding time domain sequence will be an anti-causal sequence, right? So it's not a power n u of n, it's of the form minus a power n u of minus n minus 1, that form. So if we do that, here a is minus 2, okay, if we compare with the form 1 by 1 minus a z inverse, here a is minus 2, so we get constant remains as it is 8 by 3 times, so there will be a minus 2 to the power n u of minus n minus 1, okay. And now similarly for the next term in our x of z expression, which is 5 by 3 times 1 by 1 plus half z inverse, we can find its inverse Z transform. So 5 by 3 times 1 by 1 plus half Z inverse. So now here 1, if you compare it with 1 by 1 minus a z inverse, a is minus half, okay, and here if you look at this term 5 by 3 times 1 by 1 plus half z inverse, the pole is located at z equals to minus half, okay, z equals to minus half, so mod z is half, and the ROC is mod z greater than half but less than 2. So the ROC is outside this particular pole, which is at z equals to minus half, outside of this circle. So the corresponding time domain sequence for this part of x of z is a causal sequence. So if you take its inverse Z transform, it will be of the form a power n u of n, okay. Previously we had minus a power n u of minus n minus 1 for the first term, but here since it's a causal component, it will have a power n u of n form. So a is minus half, so first the constant factor will be present as it is, 5 by 3 times a is minus half, so minus half to the power n u of n, okay, right. And now we just use linearity and add these two terms, that's it. So x of z, which was 1 by 1 plus 2 z inverse minus 5 by 3 times 1 by 1 plus half z inverse, it will have an inverse Z transform. Just need to add these two. Okay. Fine. So this is our x of n. This is our x of n. So our x of n is minus 8 by 3 minus 1 to the power n 2 power n u of minus n minus 1 minus 5 by 3 minus 1 to the power n half to the power n u of n, and we can just also rewrite this. We can take minus 1 to the power n common. Okay, so yeah, we can, since there is a minus term in front of the constants, so that minus 1 gets multiplied with minus 1 to the power n and it becomes minus 1 to the power n plus 1, and we can take out that factor as common, and in the denominator we have this by 3. We can take this whole term as a constant out, and we are left with 8 times 2 to the power n u of minus n minus 1 plus 5 times half to the power n u of n. Yeah. Okay, so you can just verify this. Okay, if it's yeah, so we found our time domain sequence. Good. Okay, now coming to 4b. So let's look at what is given in 4b. Again in 4b, in 4b we have been given our x of z, and we have been mentioned that x of n is right sided. In the previous case it was mentioned that it is absolutely summable. Here the condition is x of n is right sided. Okay, it's a hint. Similarly, this will again help us to choose our ROC. Okay, and we have been asked to use the method of long division. Okay, previously we used the method of partial fractions, but now in part B we have been asked to use long division method to find x of n. So let's do that. So we will get a flavor of how to use all these different methods, right? Okay. So here we need to use long division. Okay, and our x of z is given as 1 minus half z inverse divided by 1 plus half z inverse, and we have been given that x of n is right sided. It is mentioned. Okay, so if you observe the expression of x of z, clearly there is a pole at z equals to minus half, and so a right sided x of n implies for right sided x of n, the ROC would be mod z of the form mod z greater than mod of minus half, right? It's outside of a circle, and this circle is governed by this pole location at minus half. If you take the modulus, it's mod of minus half, which is half. So ROC is given by mod z greater than half. Okay, so remember in the lectures when we are doing this long division method, if the sequence is right sided or in fact if it's a causal sequence, okay, you can write the denominator, okay, the what do you call it, the divisor, right, by which you are dividing, okay, the numerator. So you can write it in the same order. What I mean is, so here you need to divide this numerator 1 minus half z inverse, you need to divide this by 1 plus half z inverse, this denominator. So you can write this denominator, which is our divisor, in the same order as it is given, 1 plus half z inverse, that's fine. But and this is true when the sequence is causal, or here it's right sided, it's fine. But if so, whenever the ROC is of the form mod z greater than some value, it's outside of a circle. But if the sequence is anti-causal, if the ROC is inside of a circle, then you need to write this divisor, this denominator, in the reverse order. Like if it was originally 1 plus half z inverse, you need to write it as half z inverse plus 1 and then divide the numerator. So but here we will write it as it is because it's a right sided sequence, and let's perform the long division. So we have 1 minus half z inverse. Okay, so what should be the first term in the quotient? We should multiply by 1. So if you do that, you get 1 plus half z inverse. Okay, we get minus z inverse on subtracting, and here we need to again multiply by, so minus z inverse is the remainder. Now we need to multiply this divisor by minus z inverse, and we get minus z inverse minus half z to the power minus 2. Okay, and now the remainder is half z to the power minus 2, and now we need to multiply by half z to the power minus 2. So we get half z to the power minus 2 plus 1 by 4 z to the power minus 3, right? So now the remainder becomes minus 1 by 4 z to the power minus 3, and similarly we can multiply again by minus 1 by 4 z to the power minus 3, and so on. So we get minus 1 by 4 z to the power minus 3 minus 1 by 8 z to the power minus 4, and the remainder comes out to be 1 by 8 z to the power minus 4. Yes, so and it continues, it continues in a similar fashion. So if we write down up to these many terms, we get our quotient, which is our x of z, which is this quotient term here, 1 minus z inverse plus half z inverse plus half z to the power minus 2 minus 1/4 z to the power minus 3, and so on, it continues. So you get this as okay, and so on. So this is clearly in our expanded form of x of z, right? So it is of the form summation n running from minus infinity to infinity x of n times z power minus n, which is the general formula of x of z. So, and this first term is, it corresponds to index n equals to 0, this corresponds to index n equals to 1, this corresponds to n equals to 2, and so on, this corresponds to n equals to 3. So we can directly take the inverse Z transform and write it. So all the terms corresponding to the negative indices from -1 and lower order indices, it's 0, the coefficients are 0. So we have zero. So this is the index corresponding to n equals to -1, its value is 0, and we have 1. So I will mention this arrow which is pointing at n equals to 0 index, so its value is 1, and for n equals to 1 we have the coefficient as coefficient of z inverse is -1. For n equals to 2 we have coefficient of z to the power -2 as half. Okay. Similarly for n equals to 3 we have -1/4. Okay, and so on. Okay, you can keep it like this, or else you can also express this x of z. You can write x of z in a different form and come up with a more compact expression for x of n. So let me show you. So if you just do from here, so I'm writing in another form. Okay, so what I can do is x of z is 1 minus, you can take z inverse as common, yes, you get this, and now this term inside this bracket 1 minus half z inverse plus 1/4 z to the power -2, this is an infinite GP series with common ratio -half z inverse, and since we already know the ROC, which is mod z greater than half here. So mod z, so I am writing mod z greater than half implies this minus half z inverse, which is our common ratio. This is nothing but 1 by 2 z. Okay, this is so mod z greater than half means 1 by mod z is less than 2. So this is less than 1 by 2 times 2. So this is 1. So this mod of minus half z to the power minus 1, its modulus is less than 1, and this is the condition that we need for the common ratios modulus to be less than 1 for the series, for the infinite series to converge to a finite value, right? If this is its modulus is less than 1, then only we can express it in the form of a by 1 minus r, that form we are familiar with. So anyways, I just wrote it down for checking, just to ensure that we can indeed express it in the form of a finite GP series. So we can write it in the form of, we can use the formula for infinite GP series. So I am going to the next page. So we get x of z as 1 minus, so z inverse was there in the coefficient, and if we use the formula for infinite GP series, so this minus half z to the power minus 1, it was the common ratio. So 1 by 1 minus half z to the power minus 1 is the result of that summation, and since z to the power minus 1 was already sitting in the coefficient, it is present, and the ROC is mod z greater than half. We already saw that, and now this form is known to us. Okay, so what is the inverse z transform of the first term? This, if x of z is 1, what is its inverse z transform? It's simply delta of n, right? It's delta of n. It's only 1 at n equals to 0. Okay, and for this, what is the inverse z transform? If we only consider 1 by 1 minus half z inverse, it is a known form, and the ROC is mod z greater than half. So it is of the form 1 by 1 minus a z inverse, where mod z is greater than mod a, that form. And for that kind of a right sided sequence, we have the corresponding time domain sequence as a power n u of n, and here a is half, so half power n u of n, but additionally we have a factor of z inverse multiplied, and whenever we have a multiplicative factor of z inverse in the z domain, it translates to a delay, as we know from the delay property of z transform, it translates to a delay in the time domain. So multiplying by z inverse means delaying by one sample, so x of n minus 1, so it will be half to the power n minus 1 times u of n minus 1. Okay, so this is half to the power n minus 1 times u of n minus 1, right? So therefore our overall x of n is simply, by using linearity we can write okay. So this is our final answer. So we use the long division method for part B, and now for part C again we need to use the partial fraction expansion method like we used for part A. The Z transform is given, and it has also been mentioned that x of n is again absolutely summable, similar to part A. So again we will use that known result from our lectures, that whenever x of n is absolutely summable, we know that the ROC of x of z will include the unit circle mod z equals to 1, and we will choose our ROC to be such that it includes the unit circle. Okay, so let's do that. Let's do 4C. Right, 4C, and 4C again we need to use partial fractions. Let me check if the recording is going on. Yeah, it's going on. Okay, so x of z is given by 3 by z minus 1/4 minus 1 by 8 z to the power minus 1, and it is mentioned that x of n is absolutely summable. Okay, right, again we need to factorize the denominator here for using partial fraction. So let's do that. So we can write x of z as 3 by z minus, so again we can write 1/4 as, so it's basically minus 1/4, the term sitting in the middle in the denominator. We can write it as 1/4 minus half. So let's do that. So we have okay, this is fine. Now we can just take the common terms. So z plus 1/4 minus half can be taken as common. Yes, this is fine, and so for the first term here in the denominator z plus 1/4, I can also take z common, 1 plus 1/4 z inverse minus half 1 plus 1/4 Z inverse. Okay, so you get, I can bring this yeah, I can multiply Z inverse in the numerator and the denominator. So I get 3Z inverse so I get this, and now I have the factors in the denominator. Okay, the first factor is 1 plus 1/4 Z inverse, and the second factor is 1 minus half Z inverse. Okay, yes, and this again we have successfully factorized our denominator, and now we can use partial fraction expansion to express it in form of some a by 1 by 1/4 Z inverse. This is the first term, and plus some p by 1 minus half Z inverse. Okay, let's say we can write it like this. Now we will compute the values of a and b such that this holds true. So if we just cross multiply and equate with the numerator like we did before, we can write a times 1 minus half Z inverse plus b times 1 plus 1/4 Z inverse equals to 3 Z inverse, and I am labeling it as equation 1. Now again, to find values of a and b, let's first find the value of a. For that we need to eliminate b. To eliminate b, we must eliminate its coefficient. For that we can substitute Z inverse equals to -4, okay, in equation 1. So putting Z inverse equals to -4 in equation 1, we get 3a equals -12, or a equals -4. Okay, and similarly now we will eliminate a and find the value of b. So we will put Z inverse equals to 2 in equation 1, and we get 3b by 2 equals 6, or b equals to 4. Okay, good. And now, having found the values of a and b, we can just substitute it in this form here. So let's do that. So we get our x of z as A is minus 4, 1 plus 1/4 Z inverse plus B is 4 divided by 1 minus half Z inverse. Okay, and now clearly the poles are located at Z equals to minus 1 by 4 and Z equals to 1 by 2, and depending on these pole locations again we can have 3 possible region of convergences. So the first ROC could be mod Z less than 1/4, the second ROC could be 1 by 4 less than mod Z less than 1 by 2, which is the annular region, and the third and last possible ROC could be mod Z greater than half. Okay, and out of these 3 possible ROCs, which one should we pick? Again, since in our question it is mentioned that in 4C it is mentioned that x of n is absolutely summable, we again use the fact that absolute summability of x of n implies that the ROC of x of z must include the unit circle mod z equals to 1, and therefore we should pick the ROC that includes the unit circle, and in our case it turns out to be mod z greater than half, that one. So we'll pick that ROC and then we will take the inverse transform and find x of n. So it's the same thing that we did for part A of the fourth question. So again, let us write everything clearly. Okay, so pole locations at z equals to minus 1 by 4 and z equals to half. Therefore, possible ROCs are, first one is the interior of the smaller circle, which is mod z less than 1 by 4. Second possibility is the annular region between the two circles, and the third possibility is mod z, so outside the larger circle, mod z greater than half. And now, since it is given that x of n is absolutely summable, therefore ROC of x of z includes the unit circle. So out of these 3 possible ROCs, we should pick our ROC to be mod z greater than half, right? Because this one includes the mod z equals to 1 unit circle. So the ROC of x of z is mod z greater than half. And now we can use we can just individually take the inverse transform of these two terms of x of z in the summation like we did before, and then use linearity to get the overall expression for x of n. So the first term is minus 4 by 1 plus 1/4 z inverse. So let's take its inverse z transform. So minus 4 by 1 plus 1/4 z inverse. So the ROC is mod z greater than half. Okay. So we have a right-sided sequence, and therefore the corresponding time domain sequence will be of the form a power n u of n. This z transform is of the form 1 by 1 minus a z inverse, similar to that form. So for the ROC to be mod z greater than mod a, this form we have the corresponding time domain sequence as a power n u of n. So here a is minus 1 by 4, because if we compare it with 1 by 1 minus a z inverse, you get a as minus 1 by 4. So a power n u of n becomes minus 1 by 4 to the power n u of n, and this constant factor of minus 4 is present. So we get minus 4 times, this is a power n u of n. A is minus 1 by 4. Right? And similarly, what was the second term in x of z? It is 4 by 1 minus half z inverse. Okay. So for the second term we have 4 by 1 minus half z inverse, and if we take its inverse z transform, given this ROC that mod z is greater than half, it's again of the form a power n u of n, and here if you compare 4 by 1 minus half z inverse with 1 by 1 minus a z inverse, that form you get a as half. So a power n u of n becomes half power n u of n, and we have a factor of 4 sitting in the numerator, so we'll keep that factor 4, and we have half power n u of n. Okay. So now by linearity, x of z was 1 plus 1/4 z inverse plus so this overall z transform has an inverse z transform of, so we'll take the sum of the two individual inverse transforms. So this follows from the linearity property of z transform, right? So okay, this is fine. Let me write it more clearly. My handwriting is not at all good, apologies for that. So it was half, right? Half. Okay. Yeah. So this is our x of n. So this is our x of n, and yeah, so this is our x of n. So let's go to the next page. We get x of n as this, and we can also write it as, so we can also write it as minus yes, you can write it as this. So yeah, so this is our final expression for the time domain sequence x of n. Okay, so I hope it was clear. The process was the same as we did for the part A of fourth question. Okay, so now let's move on to the next question, which is the last question for today. So before that, let me check if the recording is still going on. Yeah. Okay, so in question number 5, we have been asked to determine the inverse Z transform. Okay, and we need to make use of the power series expansion. So we know the formula of log of 1 minus w. It is given by minus of summation I running from 1 to infinity w power I divided by I, and mod of w is less than 1. Okay, in each of these subparts A and B, x of z is given in terms of a log, and with the given ROC with mod z, with the given constraint on mod z, and we need to use this power series expansion of log to find x of n, the time domain sequence. Okay, that's it. So let's use that. So it's a very simple, it's just simple mathematics. So let's do that. So we are looking at question number 5, and we need to use power series expansion. We have been given this known result, the formula of log of 1 minus omega expansion. So it's okay. And now in part A, given x of z is log 1 minus 2z with mod z less than half, okay, and we need to find x of n. So we can use this given result log of 1 minus w expansion, and we can expand this given x of z as like log of 1 minus 2z. We can expand this further using the result, given result. So we can write it as minus okay, here w is 2z basically, right? And you see that condition on the constraint on w was mod w is less than 1. So here in this case mod in this case our w is basically 2z, and mod w less than 1 is the given constraint for the expansion. So that implies mod 2z should be less than 1, and that gives us mod z less than half, which is exactly which is given in the question, right? This. So yeah, anyway, so let's continue. So we have now we can expand it. So minus of 2z plus 2z square by 2 plus 2z cube by 3 and so on. And now you can just simply take the inverse Z transform, and so minus 2z square minus 8 by 3 z cube and so on. So the first term here, it corresponds to the index n equals to minus 1, right? Because the power of z is 1, so it corresponds to n equals to minus 1. Similarly, this here corresponds to n equals to minus 2 and n equals to minus 3 and so on. So in the time domain sequence, the values corresponding to the non-negative indices, that is n equals to 0 and onwards, they are all 0 basically. So if we take the inverse Z transform, if we write x of n, you can write it as, so we have minus 8 by 3 for n equals to minus 3, we have minus 2 for n equals to minus 2, and again minus 2 for n equals to minus 1, and for n equals to 0 we have 0, for n equals to 1 we have 0, and for all other positive indices we have 0, and this arrow denotes n equals to 0 index. Okay, you can either keep it in this form, or we can also express it in some other compact form. So let's see how can you do that. So in another form, so let's see. So x of z was this, right? Minus 2z minus 2z square and so on. So if I use this, so x of z was minus 2z minus 2z whole square by 2 and so on. Okay, this is not square, it's cube, right? Okay, and now you will see that it follows a particular pattern. So you can also write it as 2 power 1 by 1 times z minus, just a second, minus 2 power 2 by 2 times z square minus 2 power 3 by 3 times z cube minus, and so on. So in general the nth term of this sequence is of the form minus 2 power n by n times z power n, right? So you can express this as a summation n running from 1 to infinity 2 power n divided by n times z power n. Okay, and now from the general formula of the z transform x of z, which is given by n running from summation n running from minus infinity to infinity x of n times z power minus n. In that formula z is raised to the power minus n, but here we are getting z to the power n. So in order to relate both of them, what we can do is we can just simply replace n by minus n, and we can change the limits. So so I can also write it as summation. First I am replacing n by minus n. Okay, so this becomes minus n in the denominator, and there is already a minus factor outside, so it becomes plus, and we have z to the power n becomes z to the power minus n. Okay, and now since n was previously running from 1 to infinity, minus 1 would run from minus infinity to minus 1, right? So this. Okay, so what we are doing is replacing n by minus n and changing the limits. Okay, this is what we are doing. Fine. So now we have expressed in x of z in our desired form, which is the general form, which is summation n running from minus infinity to infinity x of n times z power minus n. Here we have z power minus n, and we can just do the comparison to get x of n. So this is the idea. So yeah, now in general the Z transform x of z is given by n running from minus infinity to infinity x of n z to the power minus n. And we just found that x of z is n running from minus infinity to minus 1 2 power minus n by n times z power minus n. Okay, so by comparing we get, so if you just compare these two expressions of x of z, you can easily obtain the expression of x of n, right? So we get x of n is nothing but, it is simply 2 power minus n by n whenever n is less than or equals to minus 1. Okay, and it is simply 0 otherwise. Okay, so I can also write it in a more compact form, like x of n is 2 power minus n by n times u of minus n minus 1. That's it. Okay, that's the thing. So any answer is fine. You can keep it in this form. Okay, like we got here, just by a simple expansion, or you can also express it in this summation form here and find x of n in the form of u of n. So it's about observation, and sometimes in the MCQs you can have your time domain sequence in terms of the unit step function. So in such cases you might have to go with the second approach, which I just showed now. So yeah, so anyways, it should be easy for you to figure out the answer. And now let's look at the part B of fifth question. So we have x of z as log of 1 minus half z inverse times, half z inverse, and mod z is greater than half. Again, it's the similar approach as the part A. So let's solve this quickly. X of z is log of 1 minus half z inverse, and mod z is greater than half. So if we compare with log of 1 minus w, so here w is half z inverse, and mod w was less than 1 as per the constraint, right? So just look at the constraint. So mod w was less than 1. So if we use that constraint, that implies that mod half z inverse is less than 1, or if we just so half can come out, so 1 by 2 mod z is less than 1, or mod z is greater than half, right? So we are getting the same condition here. Okay, it's just to verify it. So anyways, so now we can clearly use our power series expansion formula. So we have x of z as log of 1 minus half z inverse, which is nothing but right. So we can expand this as minus half z inverse minus half z inverse whole square divided by 2 minus half z inverse whole cube by 3, and so on. Okay, again we can observe a similar pattern that we were obtaining in the previous part. Okay, so we can write this as minus half power 1 divided by 1 times z power minus 1 minus half raised to the power 2 times z to the power minus 2 by 2 minus half raised to the power 3 by 3 times z to the power minus 3 minus, and so on. Okay, and we can express it in terms of a summation. We can take the negative sign outside, n running from 1 to infinity half to the power n, okay, divided by n times z to the power minus n, right? And this is already here, z has the power minus n. It's already in the similar form as that of the general formula of x of z, which is summation n running from minus infinity to infinity small x of n times z to the power n. Okay, so here we don't need to replace n by minus n and do all those change of limits and so on. So okay, we can just now again do the comparison. So just a second. Okay, now in general, x of z is given by n running from minus infinity to infinity, small x of n times z to the power n, and we just got x of z as minus of n running from 1 to infinity half raised to the power n divided by n times z to the power minus n. Correct? Okay. So by comparing, we get x of n as, so x of n takes the form minus of half raised to the power n by n whenever the limit of n is from 1 to infinity. So whenever n is greater than or equals to 1, and it is 0 otherwise. Okay, and this can also be written in this form, minus half to the power n by n times u of n minus 1, right? Or you can bring this 2 upwards and you'll get a minus sign in the exponent, and so you get this times u of n minus 1, right? Yeah, that's it. That's it. That's the desired time domain sequence x of n we obtained using the power series method, right? Okay. So this concludes the today's live session, and we'll meet again on next Monday. So yeah, thank you. I'll stop the recording now.